Welcome back to the Deep Dive. Today, we are undertaking, well, a pretty critical mission, actually.
Oh, yeah. What's that?
We want to transform the sprawling, sometimes complex world of HashiCorp Terraform into clear, concise, and immediately actionable knowledge for you.
Okay, I like the sound of that. Terraform, it's huge.
It really is. If infrastructure as code IAC is the future of IT operations, then Terraform is, pretty much the definitive language of that future.
Exactly. I mean, for anyone working in the cloud today, mastering Terraform isn't really optional anymore, is it? It's becoming the standard.
That's what we're hearing.
Yeah. So our goal today is to dive deep into its architecture, really understand the nuanced workflow, and fully grasp the critical role of the state file.
Making sure you walk away with a true, comprehensive understanding.
That's the plan.
All right. So let's start with the problem. The operational headache Terraform was built to solve. We're talking about the ClickOps era.
ClickOps, the bad old days.
Right. This is that nightmare scenario where system administrators are logging into cloud consoles, manually clicking through menus,
Provisioning VMs one by one.
setting up networking rules, and then maybe 6 months later, having to rebuild that exact same infrastructure.
From memory, or trying to piece it together from screenshots, or worse, emails.
Exactly. Especially when, maybe the system needs an update or a migration, or maybe you tore it down overnight to save costs.
It was chaos, pure chaos, and totally unsustainable. That manual process is, well, it's slow, it's wildly inconsistent, and it's just riddled with potential for human error.
Oh, absolutely.
Think about bringing up that staging environment again in the morning after tearing it down. You mentioned saving costs, great idea, but rebuilding it could easily take 2 hours of clicking, checking, debugging, IAC, and specifically Terraform. It just ends that cycle.
So Terraform brings repeatability, it brings control, and it does it through code.
Precisely. And the market definitely reflects this need.
Yeah, we've seen those analyst reports predicting that the global revenue for infrastructure as code will hit something like, what, $2.3 billion by 2027?
Sounds about right. With annual growth around 24%, that's not trivial.
Not at all.
Yeah.
That kind of growth really confirms that IoT isn't just some trend, it's a foundational shift in the industry.
And to really leverage Terraform effectively, you first have to embrace the philosophical shift behind it.
Okay, what's that?
Moving from the imperative way of thinking to the declarative mindset.
Yes.
Yeah.
I love the analogy we often use here. The imperative mindset is like a traditional cooking recipe. Right?
Exactly. First, turn on the stove. Second, add oil to the pan. Third, crack 3 eggs. It's all step-by-step instructions.
And that's how old shell scripts worked, or, some of those older proprietary tools.
Right. And if step 2 fails in that script, you have to write all this complex error-handling logic to figure out what went wrong and where to pick up again. It gets messy fast. The declarative mindset, which is what Terraform uses, is much simpler conceptually. You just define the desired end state.
So, not how to make it, but what I want.
Precisely. I want a 3-egg omelet. That's your declaration.
And Terraform figures out the path to get there.
Correct. You define your goal in your code files like, I want 5 web servers, a highly available database, and a load balancer connecting them. Terraform Core takes that, figures out the dependencies.
Like the database needs to exist before the web servers try to connect to it.
Exactly. It builds that dependency graph. It checks what already exists in your environment, compares it to your desired state, and then only applies the necessary changes, creates, updates, deletes to reach that state.
That's the concept of idempotency.
Yes, exactly. Running the same code multiple times should result in the same end state without causing errors or unwanted side effects. It's absolutely essential for reliable automation.
And that whole declarative shift, it delivers the core benefits, the real why of using IAC. We should probably run through those main advantages.
Yeah, good idea. There are about 6 key ones. First up, infrastructure now gets version control.
Like standard application code.
Exactly like standard code. Your entire infrastructure blueprint lives in Git, or whatever version control system you use. Every single change is tracked, it's commented on, ideally it's peer-reviewed.
And if a deployment goes wrong, causes an outage,
you can instantly see the exact lines of code that changed in that commit, and you can roll back to the previous stable commit with a simple git command. It's genuinely like having a time machine for your cloud environment.
Okay, that's huge. What's second?
Consistency. No more of those, well, it works on my machine excuses.
Yeah, we've all been there.
Because the exact same code is executed everywhere. Dev, staging, prod, your environments are guaranteed to be identical, or at least as identical as the code defines them. This eliminates a massive class of environment-specific bugs.
That makes sense. Third.
Speed and efficiency. This is often where the big ROI comes in, saving dollars and engineer hours.
We heard that anecdote from one of the sources, right? About the financial services company.
Yeah, that's a classic example. They reduced a provisioning process that used to take 3 weeks down to just 45 minutes.
3 weeks.
And that wasn't just someone clicking slowly. That 3 weeks involved manual ticket creation, multiple layers of human approvals, manual error checking, security reviews, a whole chain of manual steps.
Right.
Terraform streamlines all of that into a single, automated, and importantly, auditable GitOps workflow.
Okay, number 4.
Disaster recovery. It's almost inherently built in. If an entire cloud region goes down,
Which happened.
which absolutely happens, you can simply point your existing Terraform code at a different region, run Terraform apply, and your infrastructure gets rebuilt exactly as it was defined, quickly and reliably. Your infrastructure becomes essentially disposable and reproducible on demand.
That's powerful. 5th.
The code itself becomes your definitive live documentation.
Instead of outdated wikis that nobody updates.
Exactly. When you onboard a new engineer, they don't need to hunt down questionable documentation. They can read the Terraform configuration files. That's the authoritative source of truth for what infrastructure actually exists and how it's configured.
And finally, number 6.
Collaboration. Infrastructure development starts to look a lot more like modern software development. The code goes through peer review. You can enforce standards like mandatory tagging, run automated checks.
Catching errors or security issues before they hit production.
Precisely. Proactively, not reactively.
Okay, so those 6 points really lay the groundwork. They show the value prop. Now we can dig into the machine that makes it all happen, the Terraform architecture.
Right. Let's get into the nuts and bolts.
So thinking about the landscape, every major cloud provider offers its own IAC tool, right? AWS has CloudFormation, Azure has ARM templates.
Google has Cloud Deployment Manager. Yeah.
So why did Terraform become the kind of de facto industry leader? What was the gap it filled?
The answer really lies in the multi-cloud challenge and also managing things beyond just the core cloud provider services.
Meaning?
Well, CloudFormation is proprietary AWS tech. It only speaks AWS APIs. ARM templates only speak Azure APIs. If your company has a multi-cloud strategy, maybe using AWS for compute and Azure for certain data services, or if you need to manage third-party tools.
Like what?
Like monitoring systems like Datadog or your GitHub repositories, or maybe Kubernetes clusters running anywhere, or even DNS providers.
Yeah.
You'd potentially need 5, 6, 7 different proprietary tool sets and languages to manage everything. It becomes unmanageable.
Yeah, I see. And Terraform's superpower is?
Being provider agnostic, it acts like a universal translator for infrastructure. You learn one core declarative language, that's HCL, the HashiCorp configuration language in Terraform, through its provider plugins, translates your HCL intentions into the specific API calls needed for whatever platform you're targeting.
So the same HCL knowledge applies whether I'm talking to AWS, Azure, GCP, VMware, or even, like you said, Datadog or GitHub.
Exactly.
Right.
Or a SaaS ticketing system or network hardware. Anything with an API, potentially. That's the power. Learn one workflow, one language, apply it everywhere.
Let's dig into HCL a bit more. We know it's human-friendly, but what's its actual structure like? How does it work?
Okay, so HCL is built around a few core concepts: blocks, arguments, and expressions. It's designed to be easy for machines to parse, but also, importantly, visually clear for humans to read and write.
Blocks being the main containers.
Yeah. Things like resources, variables, outputs, providers, they're all defined within named blocks, usually denoted by curly braces. Inside those blocks, you have arguments.
Simple key-value pairs.
Mostly, yeah,
Right.
like instance type equals t3.micro. But the real power comes from expressions.
Okay, expressions sound more like programming.
They allow for dynamic behavior within your static configuration files. Most common time you'll see is interpolation.
Using that syntax.
Or similar variations depending on the context, yeah. It lets you inject values dynamically. A classic example is creating a server, getting its IP address as an output, and immediately feeding that IP address into the configuration of a load balancer that needs to point to it.
Okay, so they reference each other.
Right. Expressions also include more complex logic like for loops and the count meta argument. These are absolutely critical for managing multiple similar resources without just copying and pasting the same block hundreds of times.
So you can say create 5 identical web servers with one block using count, instead of 5 separate blocks.
Exactly. Or use for each to loop over a map of configurations. That level of dynamic behavior and logic is really what sets HCL apart from just using static JSON templates like ARM sometimes feels.
Got it. Okay, so HCL is the language. Now let's break down the two critical runtime components of the architecture, the core and the plugins.
Right. First, you have the Terraform core. This is the actual Terraform command line tool you run. It's a relatively small single binary written in Go. You run it locally on your machine or in your CI/CD pipeline server.
And that's the orchestrator, the brain.
That's a good way to put it. The core is responsible for reading your HCL configuration files, parsing them, building that dependency graph we mentioned, managing the state file, which we'll get to, and generally orchestrating the entire workflow, plan, apply, etc.
But the core itself doesn't know how to actually create an EC2 instance, right?
Correct. It doesn't have the specific knowledge of AWS APIs or Azure APIs or GCP APIs baked into it. It only understands the Terraform language and the workflow steps. The platform-specific knowledge lives elsewhere.
And that elsewhere is the plugins, specifically the providers.
Yes. Providers are the key. They are separate executable programs, often also written in Go, that act as the interface between the Terraform core and the target API like AWS, Azure, Kubernetes, Datadog, etc.
So when the core decides, based on the plan, that it needs to create an EC2 instance,
It essentially hands off that instruction along with the configuration details from your HCL to the AWS provider plugin. The provider is the component that knows how to translate that high-level request, I need a t3.micro instance with these tags, into the specific low-level HTTPS API calls that the AWS control plane understands.
Okay, so the provider is the translator. But you mentioned it does more than just translate API calls.
Oh, absolutely. The provider manages the entire life cycle of the resources it's responsible for. It's not just a one-way translator. It's more like a resource custodian for Terraform.
What does that mean, custodian?
Every provider implements, for each resource type it supports, like Os Instance or Azure Virtual Network, a standard set of CR-read operations. Create, read, update, and delete.
So it knows how to fetch the current state, too.
Yes, the read function is crucial. It allows Terraform to refresh the state and see what the resource actually looks like in the cloud right now. Furthermore, the provider defines the schema for each resource.
The schema.
Yeah, it tells the Terraform core exactly what arguments are allowed for an Os instance, like AMI, instance type, tags, which ones are required, which are optional, what their data types are, and critically, which changes require forcing a replacement that white plus action we'll talk about later.
Wow, okay, so the providers are doing a lot of heavy lifting.
They really are. And the scale of this provider ecosystem is, well, it's immense. It's what truly validates Terraform's position.
Where do these providers come from?
The main place is the public Terraform registry, which you can find at registry.terraform.io. It hosts over 3,000 providers now.
3,000.
Yeah, it's huge. This includes official providers maintained by HashiCorp for the major clouds, verified tiers from partners like cloud providers or SaaS companies, and a vast number of community-maintained providers for more niche services or tools.
So you can manage pretty much anything.
If it has a reasonable API, there's a good chance someone's written a Terraform provider for it. You mentioned managing cloud resources, DNS records, monitoring tools like Datadog, even physical network gear in some cases. The usage stats are just staggering.
Like the AWS provider.
Yeah, the official AWS provider is foundational. Last time I checked, it had seen something like 713 million downloads just this year and over 3 billion downloads overall. That gives you a sense of how many people are using Terraform just for AWS alone.
Incredible. Okay, before we move off architecture and into the workflow, we need to nail down the difference between two key concepts in HCL, resources versus data sources.
Yes, this is absolutely fundamental to writing effective Terraform code. They sound similar, but they serve very different purposes.
So resources are?
Resources are the infrastructure components that you are asking Terraform to actively create, manage, and eventually destroy. They have a life cycle that Terraform controls. They're defined using the resource block in your HCL.
Like resource instance web server or resource os VPC main.
Exactly. These are the nouns that Terraform owns and manages based on your code.
Okay, so what are data sources then?
Data sources are different. They are essentially read-only queries. They're used to fetch information about existing infrastructure or external data that Terraform does not manage.
So it's for looking things up.
Precisely. You wouldn't use a resource block to define the latest Amazon Linux AMI ID because that changes all the time and isn't something you create. Instead, you'd use a data block like data Asami, latest Amazon Linux. with some filters.
And Terraform queries AWS to find that latest AMI ID at runtime.
Exactly. It fetches that information dynamically when you run, plan, or apply. Other common uses are fetching details about an existing VPC that was created manually or by another team, or maybe reading credentials from a secrets manager. Data sources let your configuration react to the existing environment without trying to manage those external things.
Got it. Resources, things Terraform manages. Data sources, read-only lookups.
You've got it. A crucial distinction.
Okay, architecture covered. Language, core, providers, resources, data sources. Let's move into the daily routine, the practical steps. The Terraform core workflow. This sequence is what engineers run constantly, right?
Every day, probably multiple times a day. The core sequence is absolutely non-negotiable. You have to run these steps in order. Init, validate, plan, apply. And sometimes, destroy.
Let's start with Terraform init. Why is this always the very first step, especially when you say clone a new project repo?
Right, and it is all about setting up your working directory. When you first check out a Terraform project or when the configuration changes its provider requirements, you run a init.
What does it actually do?
Primarily two things. First, it scans your configuration files to see which providers are required, like Oz, Google, or Random, etc. Then, it reaches out to the Terraform registry, or a configured private registry, and downloads the necessary binary executable files for those providers.
And it stores them locally.
Yes, it puts them into a hidden subdirectory called .terraform within your project folder. And these provider binaries can be pretty chunky. Like how big?
Major cloud providers like AWS or Azure, their providers can easily be hundreds of megabytes, sometimes pushing towards a gigabyte. So init can take a moment the first time.
Okay, downloads providers. What's the second key thing init does? You mentioned consistency.
Ah, yes. The terraform.log.hcl file. This is critical for teams. When init downloads the providers, it records the exact versions and cryptographic hashes of those downloaded binaries into this lock file.
And this file gets committed to Git.
Absolutely. By committing the lock file, you ensure that every other member of your team and your CI/CD pipeline, when they run Terraform edit, will download and use the exact same validated versions of the provider plugins.
Preventing weird bugs caused by one person using AWS provider v4.1 and another using v4.2.
Exactly that. It locks down your dependencies, ensuring consistency across all environments and collaborators. So, init is step one.
Okay, directory initialized, providers downloaded and locked. Next up, Terraform validate.
Validate is your quick local sanity check. It parses your HCL code and checks for basic correctness, like syntax errors, missing brackets.
Yeah, syntax errors, ensuring resource blocks have the required arguments defined by the provider schema, checking that variable references are valid, basic internal consistency stuff. It's very fast because it's entirely local.
But we stressed this earlier, what's the crucial limitation of validate? What doesn't it check?
Right. It's purely looking at the structure and syntax of your code. It does not talk to the cloud provider. It has no idea if your AWS credentials are valid, or if you misspelled a resource name in a way the API will reject, or if you're trying to create a resource that conflicts with an existing one.
So it won't catch API-level errors.
Nope. For that, you need the next, and arguably most important, step.
The heart of the workflow, Terraform plan.
Plan is the indispensable dry run. This is where Terraform actually figures out what needs to be done. It does talk to the cloud providers.
What's the first thing it does when it talks to the cloud?
It performs a refresh of the state file. It queries the APIs to get the current real-world status of all the resources Terraform is managing. Then it compares that refreshed current state against the desired state defined in your HCL code.
And the result of that comparison is the execution plan.
Exactly. It generates and outputs the execution plan, which details the delta, the exact set of actions, create, update, destroy, that Terraform proposes to take to make the real world match your code.
And the output uses those specific symbols to show the actions. Let's go through those again.
Super important to understand these. A plus sign means a resource will be created from scratch.
Okay.
A sign means an existing resource will be destroyed.
Got it.
A tilde symbol means an existing resource will be updated in place. This means the resource itself continues to exist, its ID doesn't change, but one or more of its configurable attributes will be modified.
Like changing a tag or maybe scaling up memory.
Often, yeah. Things that the cloud provider allows you to change without tearing down the resource.
And then there's the one that needs careful attention.
The goal plus symbol. This signifies a replacement. It means Terraform has detected a change to an attribute that the underlying cloud provider considers immutable after creation.
Like changing the underlying disk type or the AMI ID of a running VM.
Exactly. Those often can't be changed on the fly. So Terraform's only option is to destroy the existing resource and then immediately recreate it, plus with the new configuration. This is potentially disruptive, especially for things like databases or critical servers, so you must review the plan carefully whenever you see M+ set.
And speaking of careful review, especially in production environments, you absolutely need to use the plan saving feature, right?
Oh, 100%. Best practice, maybe even mandatory practice in regulated environments, is to never just run Terraform applied directly in production.
Instead, you run.
You run Terraform plan, outset plan, or whatever file name you want. This performs the planning logic, but saves the resulting execution plan the exact list of changes to a binary file on disk.
What's the safety benefit there?
It's huge. You can take that TF-clan file, review it carefully, maybe archive it for audit purposes, get peer approval, or run automated policy checks against it. Then, maybe hours or even days later, you can run Terraform apply TF-plan.
And it executes only the changes in that saved file.
Exactly. It guarantees that the exact plan you reviewed and approved is the one that gets executed. It completely eliminates the risk of someone accidentally modifying the .tf files between the plan and apply steps, or the risk of the cloud environment drifting further, leading to unexpected changes when apply runs its own implicit plan. It's a critical safety lock.
Okay, so plan reviewed, plan saved, approval granted. Only then do we move to Terraform apply.
Right. Apply is the command that actually executes the changes. It takes the plan, either implicitly generated or from a saved file, and starts making those API calls to the cloud providers to create, update, or destroy resources.
And by default, it asks for confirmation.
Yes, if you just run Terraform apply without a plan file, it will first generate a plan, show it to you, and then prompt you with, do you want to perform these actions? You have to type yes manually.
But in automation, CI/CD pipelines.
In those non-interactive scenarios, you'll typically use the saved plan file method, apply TF plan, or if you trust the automation implicitly, use with caution, you might use Terraform apply auto approve. This skips the interactive prompt.
Makes sense. And then for cleaning up, there's the Terraform destroy command.
Yeah, destroy is basically a convenient shortcut. It figures out all the resources currently managed by your configuration based on the state file, generates a plan to destroy all of them, asks for confirmation, unless you use auto-approve, and then executes the deletion.
Useful for temporary environments or tearing down experiments.
Exactly. And just a quick note, running Terraform apply destroy is functionally identical to running Terraform destroy. It's just an alias.
Okay, that whole workflow, init, validate, plan, apply, hinges on something we've mentioned a few times, the state file. This seems pretty central. Let's dive into state management. What is the state file?
The state file, which by default is named terraform.tfstate, is essentially Terraform's memory. You can think of it as its ledger or its single source of truth about the infrastructure it's supposed to be managing.
And it's just a file. What format?
Under the hood, it's a JSON file. It contains a detailed mapping. It links the logical resource names you use in your HCL code, like osinstance.webserver, to the actual real-world resource IDs assigned by the cloud provider, like an EC2 instance ID, I012345 ABCDef, its public IP address, its subnet ID, etc. It stores all the attributes of the managed resources as Terraform currently understands them.
Okay, why is maintaining this mapping so critical? Why can't Terraform just figure it out from the code each time?
Because Terraform needs to know what already exists to figure out what needs to change. That delta calculation during the plan phase is impossible without state.
How so?
When you run Terraform plan, the first thing it does is refresh its knowledge based on the existing state file. It looks at the state file, sees, okay, I'm managing instance I012345 ABCDef, which corresponds to osinstance.webserver in the code. Then it talks to the AWS API to get the current attributes of I012345 ABCDef. It updates the state file with this refreshed info. Then it compares this refreshed current state against the desired state defined in your HCL code.
So if the HCL says the instance type should be t3.large, but the refreshed state shows it's currently t3.micro.
Then Terraform knows it needs to plan an update action, or potentially a replacement plus, to change the instance type. Without that state file mapping resources in code to resources in the cloud, Terraform would be lost. It wouldn't know if it should create a new instance or modify an existing one.
Got it. State is the memory connecting code to reality. Now, where this state file lives is a huge operational concern. Let's talk about the danger zone. Local state?
Right. By default, when you first run Terraform, it creates that terraform.tf state file right there in your project directory. This is fine maybe for solo learning or tiny personal projects, but it is absolutely never acceptable for team environments or production infrastructure.
Why not? What are the specific problems?
There are several, and they're serious. First, collaboration is impossible. If you have the state file on your laptop and your colleague has a copy on theirs, how do you reconcile changes? You can't.
Leads to conflicts and overwritten work.
Instantly. Second, related to that, there's no locking mechanism. What happens if you and your colleague both run Terraform apply at the exact same time, both trying to modify the same state file?
Race conditions. State corruption.
Guarantees state corruption. The file will end up in an inconsistent mess, and Terraform will lose track of your infrastructure. And the third, and perhaps most critical issue, is security.
What's insecure about a local JSON file?
As we touched on with sensitive variables, that terraform.ts state file contains sensitive data in plain text.
Seriously, like what kind of data?
Potentially anything Terraform needed to manage a resource or any sensitive outputs you defined. Database passwords, private keys for servers, API tokens, connection strings. Even if you marked the input variable or output value as sensitive, equals true in your HCL.
The raw value still ends up in the state file.
Yes. The sensitive flag mainly just redacts it from the CLI output. The actual value is stored unencrypted in the JSON state file by default. If you accidentally commit that terraform.tf state file to a public Git repository, or if it leaks somehow, it's a massive security incident waiting to happen.
Okay, local state is clearly a no-go for anything serious, so what's the solution?
Remote backends. This is the non-negotiable best practice for teams.
How do they work?
Instead of storing the terraform.tf state file locally, you configure Terraform to store it securely in a shared remote location. Common choices include cloud storage services like AWS S3, Azure Blob Storage, or Google Cloud Storage. HashiCorp also offers its own managed backend with HTTP Terraform Cloud.
So that solves the collaboration issue. Everyone points to the same central state file. And presumably, these services offer encryption.
Yes, storing state in something like S3 allows you to leverage server-side encryption at rest, protecting the sensitive data within the state file. But just storing it remotely isn't quite enough for teams. You also need state locking.
Why the separate lock? If everyone's accessing the same file, isn't that solved?
Not quite. You still have the problem of concurrent writes. If 3 engineers on your team try to run Terraform apply simultaneously, even against the same remote state file in S3, they could still potentially fetch slightly stale versions and try to write conflicting updates back at the same time, leading to corruption.
The race condition still exists.
Exactly. So remote backends that support locking use a secondary mechanism. For the AWS S3 backend, the standard practice is to configure a separate DynamoDB table purely for state locking.
How does the DynamoDB table help?
Before Terraform starts any operation that might modify the state, like plan with refresh or apply, it first attempts to acquire a lock by writing an item to that DynamoDB table. If it succeeds, it holds the lock, performs its operation, updates the state in S3, and then releases the lock. If another Terraform process tries to acquire the lock while it's held, DynamoDB prevents it, and the second process has to wait.
So only one process can modify the state at a time.
Correct. It ensures strict serialization of state operations, preventing corruption in team environments. It's absolutely vital.
Okay, remote state plus locking. Got it. Now, the state file isn't just for planning changes based on code, it's also how Terraform detects drift.
Yes, infrastructure drift. This is a constant battle in real-world environments.
What exactly is drift in this context?
Drift occurs anytime your actual deployed infrastructure deviates from the state defined in your Terraform code, usually because someone made a manual change outside of the Terraform workflow.
Like logging into the AWS console.
Exactly. Maybe someone manually adds a production critical tag to a database because they needed it right now, or a security engineer modifies a firewall rule directly in the console to address an urgent issue, completely bypassing Terraform.
Okay, so the real world no longer matches the code or the last known state. How does Terraform find out?
It happens during the state refresh phase, usually at the beginning of a Terraform plan. Terraform queries the cloud provider APIs for the current configuration of the resources it manages. It compares that real-world configuration to what's recorded in its state file.
And if it finds a difference, like that manual tag?
It detects the discrepancy. If the state file, based on the last applied, doesn't have that production critical tag, but the API reports the tag is now present on the actual database, Terraform identifies this as drift.
And what does the plan output show?
Crucially, if your HCL code also doesn't define that tag, Terraform's goal is to enforce the desired state. your code. So the plan will propose an action to remove the manually added tag to bring the infrastructure back into alignment with the code definition.
Ah, so it tries to correct the drift automatically by default.
Yes, its job is to make reality match the code. This drift detection and reconciliation is a powerful feature for maintaining consistency and catching unauthorized changes.
Now, managing this detection and potential reconciliation, there were those two specific command flags we needed to clarify. They were refresh only. There's a plan version and an apply version. They sound similar, but do different things, right?
Very different operational outcomes, yes. Let's use that analogy again. Think of Terraform plan refresh only as performing an audit.
It's an audit.
Yeah. When you run plan refresh only, Terraform performs the state refresh. It talks to the cloud, finds out the current reality, notes any drift compared to the state file, and updates its memory, the state file, with that current reality. But critically, it stops there. It reports the drift it found, but it does not generate or propose any changes to modify your actual infrastructure.
So it just tells you, hey, drift was detected here, and updates the state file's memory, but doesn't try to fix it.
Exactly. You're purely gathering intelligence on the current state of drift without making changes.
Okay, so that's the audit. What about Terraform apply refresh only? That sounds like it does something.
It does, but maybe not what you'd first expect. Think of apply refresh only as performing an acceptance of the drift.
Acceptance.
Yes. Let's say you ran the plan refresh only audit, saw that manual tag was added, and you decide, actually, that manual tag should be there. The security team added it for a good reason, and I want Terraform to know about it, but I don't want Terraform to remove it.
So you want to update Terraform's understanding to match the drifted reality without changing reality itself?
Precisely. In that scenario, you run Terraform apply refresh only. This command performs the state refresh, sees the drift, the extra tag, and then updates the Terraform state file to include that tag, effectively accepting the manual change into Terraform's official record. Crucially, it makes no changes to the deployed infrastructure itself. It just brings the state file into alignment with the detected reality.
Got it. Plan refresh only, audit, detect, plus update state report, no infra change. Apply inif refresh only. Acceptance, detect plus update state, no report, no infra change.
That's a good summary. 2 ways to reconcile the state file with reality, but neither actually modifies the cloud resources.
Excellent clarification. Okay, let's pivot now. We understand the core mechanics. How do we make our Terraform configurations scalable, flexible, and maintainable in the long run? This brings us to advanced configuration topics, starting with input variables.
Variables are absolutely fundamental to avoiding hard-coding values directly in your resource blocks. They are the primary mechanism for parameterizing your configurations.
Making them reusable across different environments.
Exactly. You define a variable, say variable instance count, type number, and then reference it in your code using var.instanceCount. You can then provide different values for instance count for your dev, staging, and production environments using the same core resource definition. It prevents duplication and makes updates much easier.
And variables aren't just simple values, right? What types are supported?
Terraform supports the basic primitive types you'd expect: string, number, and bool, Boolean true-false, but it also supports complex collection types: list, ordered sequence of same-typed items, set, unordered unique items, and map, key-value pairs where keys are strings and values are strings.
And there's object, too. How is that different from map?
Yes. Object is more structured than map. While a map is just string keys to string values, an object allows you to define a specific schema, like a struct. You define the expected attribute names and their specific types, which can be primitives or other complex types. This is crucial for creating robust, reusable modules where you need to enforce a specific input structure. Mastering the difference between map string and object number is key for advanced use.
Okay, complex types are powerful. Now, for people debugging why a certain value is being used, especially in CI/CD, understanding the variable precedence order is vital. How does Terraform decide which value to use if it's defined in multiple places?
Yes, this trips people up. Terraform has a strict hierarchy for loading variable values. The absolute highest priority, overriding everything else, is a variable value set directly on the command line using the nisvar flag, like Terraform apply nisvar instance count 5.
Okay, command line wins. What's next?
Next highest are values loaded from any custom.tfrs files specified using the desvar file flag, like nisvar file production.tfrs.
Got it.
Below that, Terraform automatically looks for and loads 2 specific file names in the current working directory. First, it loads terraform.tfrs if it exists, and then it loads any files matching the pattern. auto.tfrs, like network.auto.tfrs, compute.auto.tfrs. These are loaded alphabetically.
So auto-loaded files are below explicitly specified var files.
Correct. After the auto-loaded files, Terraform checks for environment variables. Any environment variable starting with a prefix, tfvar, followed by the variable name, like tfvar instance count 3, will be used.
Okay.
If the variable still hasn't received a value after all that, Terraform looks for a default value defined directly within the variable block in your HCL code.
And if there's no default either?
Then, as a last resort, if the command is running interactively, Terraform will prompt the user to enter a value for the variable. If it's not interactive, like in CI/CD, and no value is found, it's an error.
Wow. Okay. So CLI flag -var file terraform.tfrs.auto.tfrs environment vars default prompt error, knowing that order is key for debugging unexpected values.
Absolutely critical.
Now, we mentioned sensitive data earlier with stage files. Both input variables and output values support being marked as sensitive true. What does that actually do?
Marking a variable or output with sensitive true is primarily a display mechanism. It tells Terraform to redact the actual value when it shows plans or applies changes in the terminal output or in logs. You'll just see sensitive value printed instead of the actual password or API key.
So that hides it from shoulder surfing or accidental log exposure.
Yes, which is necessary and good practice. But, and this is the crucial warning we have to repeat, if that sensitive value is actually used by Terraform to configure a resource, or if it's an output value derived from a resource attribute,
it still ends up in the state file.
It still ends up stored in plain text in the terraform.tf state file, even if marked sensitive. That sensitive flag does not encrypt the data at rest in the state. This underscores, again, why protecting your state file, preferably with remote backends using encryption at rest, is absolutely paramount.
Okay, message received on state file security. Now, speaking of output values, what's their main purpose?
Outputs are how your Terraform configuration communicates useful information back to the user or to other systems after resources have been created or updated.
Like telling you the public IP address of the web server you just created.
Exactly. Or the connection endpoint for a database, or the ARN of an IMM role. You define an output block in your HCL, give it a name, and specify the value, usually referencing an attribute of a created resource. After a successful apply, you can query these values using the Terraform output command, or they can be consumed by other Terraform configurations using remote state data sources.
And they can also be marked sensitive, presumably for things like generated passwords.
Yes, output blocks also support sensitive true for the same reasons redacting the value from console output while still storing it, potentially, in the state.
Okay. Now for the big one for large-scale infrastructure. Modules. How do they help manage complexity?
Modules are the cornerstone of creating reusable, maintainable, and understandable Terraform code bases. They're essentially Terraform's way of creating abstractions, much like functions or classes in traditional programming.
So instead of having one giant main.tf file with thousands of lines.
Right, which becomes completely unmanageable, a nightmare of spaghetti code. A module is simply a collection of standard .tf configuration files grouped together in a dedicated directory. This module encapsulates a logical unit of infrastructure, maybe a standard VPC setup or a secure database configuration or a reusable web application stack.
And then your main configuration just calls that module.
Exactly. Your root configuration becomes much simpler, primarily consisting of module blocks that call these reusable components, passing in variables to customize them for the specific environment, dev, prod, etc. It promotes DRY, don't repeat yourself, and makes the overall architecture much clearer.
Where do these modules typically come from? How do you reference them?
There are a few common sources. For simple project-specific modules, you might just store them in a subdirectory locally, like .modules VPC, and reference them with a relative path. This is fine for tightly coupled components within a single repository.
But for shared modules across teams or projects?
For shared components, the best practice is usually to store them in their own dedicated Git repositories. You can then source the module directly from Git in your Terraform code. And critically, you should always reference a specific version tag or commit hash, for example, using the .reffz 1.2.0 syntax in the source URL.
Why the specific version?
To ensure stability and predictable deployments. You don't want your production environment suddenly breaking because someone pushed an incompatible change to the main branch of a shared module you were implicitly tracking. Pinning to versions is essential.
Makes sense. And the third source?
The public Terraform registry. This is where you find well-maintained, often community-vetted modules for common infrastructure patterns, like the popular Terraform Oz module's VP-Cause module for creating standardized VPCs on AWS. Sourcing from the registry is often the easiest way to leverage best practices for standard components.
Great. Okay, one last bit on configuration before we look at enterprise features. Dependencies. Terraform is usually pretty good at figuring out the order automatically, right? Implicit dependency.
Yes, most of the time it just works. If resource A's configuration references an attribute of resource B, like a subnet needing the ID of the VPC it belongs to, vpc auth svpc.main.id, Terraform automatically understands that resource B, the VPC, must be created before resource A, the subnet. It builds this dependency graph implicitly based on these references.
But sometimes that implicit link isn't there.
Exactly. There are cases where one resource needs to be fully available before another one starts, but there's no direct attribute reference between them in the configuration. A common example might be provisioning an IAM policy attachment. You want to be sure the IAM role exists before you try to attach the policy, even if the attachment block doesn't directly reference the role's ARN in a way Terraform understands as a dependency. Or maybe an application on an EC2 instance needs to connect to a database user that's created separately.
So how do you force an order in those cases?
That's where the depends on meta argument comes in. You can add depends on all Ausium role.example to your policy attachment resource, for instance. This creates an explicit dependency, telling Terraform directly, do not even start creating or modifying this resource until the resources listed in depends have been successfully completed. It's a way to handle those hidden or timing-sensitive dependencies. Use it sparingly, as overuse can slow down plans, but it's essential when needed.
Got it. Implicit is preferred. Explicit via depends on when necessary. Okay, we've really covered the open source CLI and its core concepts in depth. Let's shift gears slightly and talk about the enterprise features offered by HashiCorp's commercial products. HCP Terraform Cloud and Terraform Enterprise. What do these add on top?
Right, these platforms are specifically designed to address the challenges of using Terraform at scale within larger organizations, focusing on collaboration, governance, and operational efficiency.
And the fundamental organizing concept in HCP Terraform is the workspace, right? But we need to be super clear. This is different from the old CLI workspaces.
Absolutely, critical distinction. The original Terraform workspace commands in the CLI were a way to manage multiple state files for the same configuration code within the same directory, often used for dev staging prod separation. That pattern is largely discouraged now in favor of better approaches like directory separation or branching.
So what is an HCP workspace?
An HCP workspace is a core concept within the Terraform Cloud or Enterprise UI and API. It represents a distinct environment or project. Think of it as a container.
What does this container hold?
Each HCP workspace has its own dedicated configuration source, linked to a specific Git repo and branch tag, its own distinct set of input variable values securely stored, its own complete run history, every plan and apply ever executed, and, most importantly, its own securely isolated state file.
So it automatically handles the remote state and locking for that specific environment.
Exactly. It provides that perfect isolation between, say, your production web app workspace and your development database workspace, even if many engineers are working across both.
These platforms also change where the Terraform commands actually run, moving to remote execution, correct?
Yes. This is a major benefit, especially for security and consistency. Instead of running Terraform applied directly from a developer's potentially insecure laptop, which relies on whatever local credentials and tool versions they happen to have, the trigger runs within the HCP workspace. The actual plan and apply operations execute on HashiCorp's secure, managed, ephemeral infrastructure, or your own self-hosted agents for enterprise.
What's the advantage there?
Consistency is key. Every run uses the same Terraform version and environment. Security is also huge. Sensitive cloud credentials can be stored securely within HCP Terraform and only injected into the temporary run environment rather than being distributed to every developer's machine.
Okay, that makes sense for large teams. But the feature that really seems to elevate Terraform into a true enterprise governance tool is Sentinel. What is policy as code in this context?
Sentinel is HashiCorp's embedded policy as code framework. It allows organizations to define and enforce specific rules and guardrails on their infrastructure before any changes are actually applied.
How does it integrate into the workflow?
Sentinel policies are typically configured to run automatically within an HCP Terraform workspace right after the Terraform plan phase finishes, but before the Terraform apply phase is allowed to start. The plan output is fed into the Sentinel engine.
And what kind of rules can these policies check? Give us some practical examples.
Oh, all sorts. You could write a policy that says, hard mandatory. All S3 buckets created must have server-side encryption enabled. Or maybe soft mandatory. No EC2 instance type larger than T3.large is permitted in any workspace tagged as development. Another common one, advisory. All resources must contain a cost center tag and a team owner tag.
You mentioned 3 different enforcement levels there: advisory, soft mandatory, hard mandatory. How do they work?
Advisory policies just print a warning message during the run if the policy is violated, but they don't stop the deployment. They're purely informational, like a gentle suggestion.
Okay.
Soft mandatory policies will block the deployment by default if violated. However, they allow for a defined override process, perhaps requiring a specific manager or team lead to approve the run despite the violation, usually with a required justification comment.
So a controlled exception mechanism.
Right. And finally, hard mandatory policies are absolute. If a plan violates a hard mandatory policy, like trying to create an unencrypted S3 bucket when the policy forbids it, the run fails immediately. There is no override possible. The configuration must be fixed to comply before it can be applied.
Wow. That really moves Terraform beyond just automation and into proactive compliance enforcement. Automated infrastructure safety nets.
Precisely. It allows organizations to codify their security standards, cost controls, and operational best practices, and have the system automatically enforce them.
Okay, fascinating. Before we wrap up, let's quickly touch on 2 advanced CLI commands that address specific operational scenarios often encountered in the real world. First, dealing with existing infrastructure. Terraform import.
Right. Import is the tool you use when you have existing cloud resources, maybe created manually years ago, or by a different tool that you now want to bring under Terraform's management.
Okay.
This is often called managing brownfield infrastructure.
How does it work? Do you point it at an existing VPC and it generates the code?
That's the common misconception. Terraform import does not generate HCL code for you. What it does do is require you to first manually write the HCL resource block that you believe corresponds to the existing resource. Then you run the import command, providing the address of that HCL resource block and the real-world ID of the cloud resource, like the VPC ID.
And what does the import command actually do then?
It talks to the cloud provider, fetches the current configuration of that existing resource ID, and then populates the Terraform state file, creating the mapping between your manually written HCL code and that real-world resource.
So it only updates the state file. The burden is on the engineer to write accurate HCL first.
Exactly. It's a multi-step process. Write code, import state, then run plan to verify your code accurately matches the imported state. Ideally, the plan shows no changes. It's powerful for bringing things under management, but requires care.
Okay. And the second command deals with replacing resources, specifically moving away from an older, riskier command.
Yes. Historically, if you wanted to force Terraform to destroy and recreate a specific resource, maybe because it got into a weird state, people sometimes use Terraform taint. Taint marked a resource in the state file as tainted, forcing a replacement on the next apply.
But that was risky.
It could be because the tainting action happens separately from the planning. You might taint something, forget about it, and then be surprised when a later plan and apply unexpectedly destroys and recreates it.
So what's the modern, safer approach?
The recommended way now is to use the Terraform apply-place resource.address flag. For example, Terraform apply-place awesome instance.web server.
How is that different?
This flag tells Terraform during the planning phase of that specific apply command to explicitly mark that particular resource instance for replacement. The resulting plan will clearly show the back plus action for that resource. It integrates the replacement decision directly into the plan and apply cycle for that run, making it much more explicit, deliberate, and visible. It's the preferred method for forcing replacements now.
Got it. Deprecate taint. Use apply replace. Excellent. Well, that was truly a comprehensive deep dive. We've gone from the core philosophy of IAC and the declarative model
through the architecture, the core, the providers, the critical difference between resources and data sources.
Walk through the essential daily workflow of init, validate, plan, apply.
Stressed the absolute necessity of remote state and state locking for any kind of team collaboration.
Covered how variables, outputs, and modules provide flexibility and reusability.
And finally touched on enterprise features like HCP workspaces, remote execution, and the powerful governance capabilities of Sentinel policy as code, plus those advanced CLI commands like import and apply replace.
Yeah, we really covered the ground. And thinking back, we started this deep dive by noting the high costs, the slow pace, and the error rates associated with that old manual ClickOps way of managing infrastructure.
A painful memory for many, I'm sure.
Right. But I think the ultimate, perhaps provocative insight we've arrived at today really comes from that discussion around Sentinel and policy as code.
It's that shift, isn't it? From just using code to make infrastructure to using code to govern infrastructure.
Exactly that. Consider the full implication here for a moment. What does it truly mean for your operations, for your security posture, when the system itself, Terraform with Sentinel, is not only capable of detecting human error after the fact, like infrastructure drift,
But can also automatically prevent non-compliant infrastructure changes like that unencrypted S3 bucket or that oversized VM from ever reaching the cloud in the first place thanks to a hard mandatory policy.
it feels like it transcends simple automation. It's moving into a realm of proactive, embedded infrastructure safety and control.
Yeah.
It fundamentally changes the game, and maybe even the role of the infrastructure engineer, moving more towards defining and enforcing these policies.
It's a powerful thought, isn't it? That really defines the mastery level of leveraging this whole ecosystem. It's not just about speed anymore. It's about guaranteed safety and compliance through code. So for those of you listening, ready to apply all this knowledge, don't be intimidated. Start practicing that core workflow in the plan, apply, get comfortable with it, and please set up a basic remote backend, even just for yourself using S3 and DynamoDB right away. Get out of local state mode immediately.
Excellent advice. Happy terraforming, everyone. We'll catch you on the next deep dive.